Alright guys, this is Unit 6, Lesson 9. This is the last lesson of this unit. So today we're going to talk about geometric sequences. So we first encountered sequences in Unit 4, and we just said they were a list of numbers in some particular order. And we studied the arithmetic sequences, where each number in the list was generated by simply adding the same quantity to the previous list. And remember, we did recursive formulas and explicit formulas. So we're going to just do a little warm-up here, remembering what sequences were. So we have the arithmetic sequence defined by the recursive formula. Remember, it tells us the first term. The first term is 5. And then each term, what we do is we take the previous term. So we have n, and then the term before that would be n minus 1. Then we add 3 to it. It's that simple. So they want you to find the next 3 terms, so A2, A3, A4. So do that now and just do part A. All right, how'd you do? Did you get something like this? Maybe like this. It's here, I promise. There it is. So you can see what was done. Pretty simple. Is that for a sub 2, you would take a sub 1 and add 3 to it. A sub 1 is 5, so now you add 3 and get 8. And some of you guys probably didn't show all these steps, but as long as you have some work where you said a sub 3, and then maybe you skipped the step and you just said 8 plus 3, but you got to get an idea of showing work. So if you skipped here and said a sub 3 is 8 plus 3, that would be enough. And then a sub 4 obviously was the 11 plus 3, which is 14. All right, now before you do part B, I don't want you to just instantly find a sub 20. Also notice it says without listing all the 20s, so we can't just keep finding them. What we want to do is see if you could remember how to do the explicit formula for this sequence. So I want you to first come up with a general formula like this for the explicit formula, and then use it to find a sub 20. So please try that now, even if you're not quite sure. See if you can remember. All right, let's see how you did with question B. So the formula should have looked something like that. Remember, the way you do explicit formula is that now we're talking about any number you want, not just the previous one. There's no term in here, so the terms are generated by a sub n. So there's no a in here, we're just talking about n itself, not a sub n. So we take the number 5, and we're adding 3 to it. How many times? 1 less than whatever we're starting with. So this is the explicit formula. If you don't remember, we need to do a little review on that. And then now we're just going to plug in a sub 20. So there we go. And then it would be simple from that. So really, we're going to do 5 plus 3 19s, keep going, and there's the total. So the work would look something like that. So that was arithmetic sequences because we're just adding 3 each time to these. Okay, let's move on. All right, now what it says is clearly arithmetic sequences share many characteristics of linear functions. It's very true. Arithmetic sequences are linear functions. In fact, arithmetic sequences are examples of discrete linear functions. Exponential functions, remember that's what we've been working with, have their own discrete versions, and those are called geometric sequences. So what you need to link, and this is important, is that arithmetic sequences are linear functions, and exponential functions are geometric sequences. So we have to get that together. And here is a formula for your geometric sequences. So we have to give the first term like we always did. Then each other term is simply taking that previous term and multiplying it by some r, where r is a constant known as the common ratio. So for the arithmetic, it was taking the previous term and adding something. Now we're just multiplying something, which you know if we're multiplying it over and over again means exponential. All right, so this exercise 2 should be fairly easy. For each of the following geometric sequences, identify the common ratio and give the next 2 terms. So you have to come up with what they're being multiplied by and come up with the next 2 terms. So hit pause and do that now, please. Okay, how'd you do? You should have got something like this. Okay, so the first one, r was 3, 54 and 162. R is negative 5, which is negative 500 and 2500. And the part C is 1/2, which would be 2 and 1. The easiest way to come up with this R, if you can't quite see it, is take the term above it, 6, and then divide it by the previous term, 2. That will work every time. You see you get 3. So over here I could do something like 100. Take the term before it, divide it by negative 20, and you'll see you get negative 5. So that always works if you can't see the pattern. And as with arithmetic sequences, we should be able to predict any particular term in the geometric sequence by thinking about how many times we multiply. So basically it's saying we should be able to come up with an explicit formula for these geometric sequences also. Alright, so we have considered the sequence below. Here is a recursive rule, meaning it would just generate one term, the next term. It says that the first term is 3, and then what we're going to do is take the term before and multiply it by 2. So when it has the b of n, that's when you know it's talking about a term. b of 1 is the first term. b of 2 is the second term. So you could tell this is a recursive formula because it's bn is a certain term number. Okay? So you guys should be able to easily find b sub 2, b sub 3, b sub 4 with this formula right there. So do that now, please. Okay, how did you do? Should have got something like that. And you can see for b sub 2, you take b sub 1 and multiply it by 2, which b sub 1 is up here. 3 times 2 is 6. Now again, a lot of you guys probably didn't show this step or some of these steps here, but if you look at this, this will help us for this next part over here. So b sub 3 says take b sub 2 and multiply it by 2. Remember, b sub 2 is 6, and really this 6 right here is 3 times 2. So notice that we're multiplying 3 by 2 2's, which was the beginning 3 we started with. Up here, we multiply it by 1 2. b sub 4 would take the 12 and multiply it by 2. Remember, the 12 was really all this stuff. So now you can see there's 3 2's. So you can see a pattern here, and this is basically like the geometric functions that we've already done. So now I want you to see, before you answer this question, I want you to come up with an explicit formula for this sequence. Could you come up with an explicit formula that would generate any number? And notice the pattern here. You can see it right in here. It's pretty simple if you see these 2's compared to these numbers here. So come up with an explicit formula and then use it to find b sub 10 and b sub 20. So do that now, please. All right, how did you do? Let's see. So here's the formula you should have come up with, and hopefully this makes sense. So if you notice what we did, for any number, we took 3 and multiplied it by 2, but the amount of 2's was 1 less than whatever the n was. So this is 2 to the second power, this is 2 to the third power. So if I took my n and minus 1, that's how many 2's there are. So again, start with my 3 times 2 by the 2's are equal to 1 less than whatever we're starting with. And you can see if I put 1 in here, this would become 0, and this would cancel out, and I'd still have my first term as 3, so that would kind of work out. So we have to be able to come up with this sequence formula on your own. And then from there, we could use that to fill it in. So we would find b sub 10, which really means 10 minus 1, so you would do 2 to the 9th power, and you got the 1536. And then b sub 20 would be the same thing. Take the 3, multiply it by 2 to the 19th power, because that's n minus 1, and you got this 1,572,864. So this is important. Hopefully you can get that down. All right, let's move on. All right, so here we got some word problems. We're going to compare the 2 different types of sequences. So basically in exercise 4, you have just won a very strange lottery. The lottery promises to give you money for each day for 30 days a month based on 2 options. So option 1, you can receive $1,000 on the first day, $2,000 on the second day, $3,000 on the third. This is an arithmetic sequence because you're just adding $1,000 each time. Option 2 is you can receive 1 penny, 1 cent on the first day, 2 cents on the second day, 4 cents, 8 cents. Now notice this is geometric because we're not adding the same amount. It looks like we're multiplying. We're simply doubling, right? Times 2, and so on. So that's a geometric sequence, or an exponential function versus a linear function. Very important that you could do those. Of the 2 options, which would result in a larger payoff for 30 days, show all the work that supports it. Now what I want you to do is to actually come up with a explicit formula for this option 1. Now this is arithmetic, so that might help. And then an explicit formula for the geometric sequence. And then use those, obviously, to find the 30th day, so that would be plugging in 30. See if you could do that now, please. All right, so for the arithmetic sequence, so here would be your general formula, explicit formula. So I could take any number, I'm adding 1,000 plus 1,000 for each new day. So day 2 would add a new 1,000, right? Day 3, I'd have 2 of them. So remember, basically, you have to remember that you're adding that sum one less time than whatever you're starting with. So if I wanted to find ace of 30, basically I'm going to have 29 thousands added on to that initial 1,000 that we started with, because ace of 1 was 1,000. Day 1 you got 1,000. So you ended up with 30,000, which makes sense after 30 days, getting 1,000 each day. All right, let's see how you did with the geometric sequence, kind of more difficult. So remember, what you do is you take your initial amount and you multiply it by your multiplying factor, this time 2, and then to a power. That's why it's an exponential function, because your variable is an exponent, one less time than whatever your n is. So your ace of 1 was 1 cent, and then we're going to double that 29 times, and you get 5 million. So you could see exponential functions and geometric sequences grow way faster than arithmetic and linear functions. And that's kind of what it says down here. Okay, so if you want to write that in there, so hit pause and do that if you need to. Almost there. All right, now it looks like we're going to just do some basic graphing stuff here. So for this one, we're just going to get into discrete exponential function. So for a geometric sequence, ace of 1 is 16. Notice what this is saying. So this means the previous term, not the number n, but the term, multiply it by half. So that is exponential since we're multiplying. List the first 6 terms. So do that first, and then we'll plot it in the graph. So could you come up with the first 6 terms of this function? So do that now. And that should look like this. Pretty simple. So ace of 1 was 16, and then you're just multiplying by half each time, so that should be easy. Now you need to recognize these as points also. So this is your input, the 1, you're putting in the first term, and you're getting out 16. The second term, you're getting out 8. So you should be able to recognize them as points like this. Okay, so I put in 1, got 16. Now I'm not putting really the number 1 in. What I'm saying is this is the first term is 16. The second term is 8. The third term is 4. And now you can be able to graph those. So go ahead and plot those on the graph that's provided. So hit pause and do that now. And it should look something like this. Pretty simple, and you can see that that gives us that exponential curve that we've talked about. Sorry, hard to do it on the computer there, but it looks something like that. All right, hopefully that went okay for you. If you struggled with this, then please get help in class tomorrow.